This is Sharmistha. I'm happy to present Differential Privacy at Scale in DSS Saloon. I work as a senior manager in data sciences at Publicis Sapient. I'm also an author and blogger and a Google developer expert in machine learning. So let's look at what is there in the agenda today. So first we will take a brief introduction to differential private systems. Then we will look at how differential privacy is used in different types of the industry, mainly in the software industry. We'll move on and look into the importance of differential privacy in location-based systems. And in that context, we will touch base upon vehicular systems in general. We'll see what are the main design considerations in building differential private systems. And in the end, we will talk about differential private systems for fog and edge computing. So what is differential privacy and why it is needed at scale? So differential privacy, as we know, is to measure how different two different data sets are. So on the left-hand side, we can see there are the two images, bottom and top, are mostly the same, except the left-hand extreme diagonal, where the image of a lady and whereas it is the image of a millennial boy. So other than that, all the images or the faces are same. So we measure differential privacy by seeing that when this data says different in terms of a single record, how much they are statistically indistinguishable. And that's how we incorporate and use the metrics called the privacy budget, which measures the ratio between the two different data sets should not differ to the degree of e to the power epsilon. That's the privacy budget. And also the sensitivity between the two different data sets, or the amount of noise added, is bounded by this max of Q of D1 minus D2. Now, how do we build this private systems in a large scale when we have to deploy models at production using Kubernetes or any other deployment tools? So we have to ensure when we deploy differential private systems using large scale big data processing pipelines like Apache Spark, we have to consider privacy before even compressing the data, checking the credential and access rights when the data gets stored in the database, and the protected private data is properly obfuscated using Gaussian or Laplacian noise, so that there is no leakage of sensitive information from the machine learning model. And ultimately, from the model, we are able to get the predictions, and we should be able to reconstruct the data back so that we can improve upon the model accuracy and other metrics. So let's look into the step-by-step and the different types of differential private systems that are available. So in general, we see that local and global differential private systems are available, and they are also governed by the same statistics that the ratio between the two data sets should not exceed e to the power epsilon. What local differential privacy does is the individual owners or the mobile clients or individual cloud owners, even we can say, are capable of adding noise, and they don't trust a central authority or a curator. And once the noise gets added, the data remains anonymized or perturbed, and it is used to build a model, or it can be used for other training purposes. But for global differential privacy, it is entirely the task of the trusted curator or the central governing authority who is responsible in adding noise from after getting the data from individual users. So after the data is perturbed by the trusted curator, the data can be used to build model. The training data can be used to build model, and after model building, even that trusted curator can be capable of and first getting the data or for audit purposes or for any other purpose. But both of these systems have the major requirement that randomized noise needs to be added, and and it ensures plausible deniability, so no one from outside, like an attacker or during adversarial attacks, can point out that this data belongs to this data set, or even a single user's information. It should not get leaked. So what are the mechanisms that are available that we can build scalable systems with differential private systems? So one of those major research which has happened is in the field of assembly modeling. So Bolton Dipping has come up with a very good metrics, performance metrics in terms of both accuracy as well as in privacy. And it is used with a stochastic gradient descent to be able to build assembled models that can sit on the top of an RDMS. It as this has assembled modeling, like if for a retail store like Walmart, we collect data from individual stores, put it into the DB, do stochastic gradient learning in terms of stochastic gradient, and ultimately the weights gets added, and after the weights get get added to a central model, the noise is added post the model training. So since noise gets added as the post model training, it's a post convergence method, and it preserves the individual relationships in the training data, like individual customer who are buying different subsets of product from a main product group, or say a retailer who is selling a different line of items along a particular category. So those information which we find in the training data gets stored, does not get obfuscated, or does not get does not lose the relationships because of adding noise post model convergence. So what are the characteristics we see in Bolton DP in modeling privacy? So Bolton DP injects noise post model convergence, as we have talked about. So the perturbation or the randomization is at the output, and that assures L2 sensitivity. So L2 sensitivity gets addressed best through Bolton DP, which has not been addressed in previous machine learning modeling, which adds differential privacy. So it has limited learning rate, so it is more fast, it is more scalable, robust. It executes in 4x speed compared to other previous models. It has a convex loss function. And the trade-off between accuracy and privacy is also very limited. So nobody has to sacrifice accuracy a lot to have a privacy assurance. So it is easy to integrate, and it's a more of an assembled prediction, like training different models separately and converging them and assimilating them. So it has been able to incorporate customer trust, because customers are more customer data or retailers data are more easily available to build models. Then what is the value addition we see for differential privacy using Bolton model in scalable distributed system? So it has more, as we talked about trust and privacy performance, it has been like, it is like, it it assures the legal contracts or the partners with greater performance as well as legality, like that we comply by the GDPR or the individual countries' privacy laws, as siloed models, as built models are built with siloed data, and there is less chance of a model getting susceptible to adversary attacks. So more partnerships in terms of service providers or contractors have better faith or trust in terms of who are the differential privacy providers or the algorithms, the ML providers. So that has been a great benefit to the business. So here we see what are how do we train different types of models without differential privacy with DP as well with Bolton DP. So the first one on the left hand side, you can see it's just a plain inductive model with sigmoid activation function, binary cross entropy, and which we are optimizing using kernel regularization on the metrics accuracy. The same thing when we do with Bolton DP, we see we have a regularization factor, radius constant, as well as we import the Bolton model. So for Bolton DP, we don't have to do much things, just importing the Bolton model and specify the stochastic gradient classifier, stochastic gradient learning, and the strong cross convex binary cross entropy will help us to build the model. It's not much, just importing the library, console library, and 3 to 4 lines of code. Whereas for normal differential privacy, we use the Gaussian or the Laplacian optimizer for adding noise, and we clip the gradients so that each individual point's contribution to the total differential privacy model is not too much. So the attacker won't be able to distinguish the model or get access to the confidential data of a single user. Then we have micro batches, as differential privacy works with TensorFlow, micro batches, like learning rate and noise multiplier. So if you need to go into more of the details of these things, we can have a look at TensorFlow privacy, how this, what these factors are, how the gradient clipping happens, what are the noise multipliers, and why the learning rate and micro batches are important in training models without using Bolton DP, but using plain differential privacy. Now let's have a look at what are the industrial systems that have differential privacy incorporated. So we see energy systems, transportation systems, industrial IIoT, or healthcare systems all have sensitive data coming up from the IoT sensors. And these data are all very confidential because patient's health record might have his heart disease or his skin problem or his liver problem. We cannot expose this data to the general public or even to attackers. Similarly, with transportation systems, with the coming of the GDPR, we are now abiding by many laws, and we give very protected user interfaces. Friendly user interfaces are designed where the interface, the mobile interface, will ask the user whether is it okay we take your location information, or you want privacy to be guaranteed, at what level of granularity do you want your GPS information to be available with us. Since there are so many laws, and other without the laws we end up in a heavy penalty or even in jail. So we have to be very strict while we build machine learning models using those sensitive data. And as you can see, like for all the systems, we have to have a proper ML model which incorporates privacy before having the predictions or the models being getting deployed onto the cloud. So one of the most important factors, as we have talked about, some of the sensitive informations include credit card, age, bank details of individuals, sensitive records from companies which have like IoT sensors capturing images or videos of sensitive places of the within the organization, or even taking healthcare records, or even energy systems, utilities. What are the new things that are getting explored that should not get leaked to the general public? And this personal data can be of different levels. Maybe it is name, address, or social security, or it is related to date of birth, zip code, medical records, IP addresses, or even the data can be linked with different individuals. We have seen there are attacks to IMDb and Netflix databases where through linking attacks, where attackers have been linked, have been able to link individuals which are similar by comparing their ratings and compromising one system where users personal information have been available. So by linking similar kinds of users, they are also able to get individual information. And this kind of first three levels we have seen, and even not related to personal but census data related to weather. So if somehow the weather information gets leaked and the attacker can map back to the location, so that also information needs to be protected in large scale distributed systems. So what are the major industry giants who have already deployed differential private solutions that are available in the market? One of them are Google and Apple. So the wrapper has been implemented in Google Chrome browser that collects data from millions of users every day, and to track that what is the homepage of the user, what are the search engine, what are the search terms they are using, and it is at a local differential at a level of local differential privacy. So the noise addition is at the individual side where the data is collected. Now, this measure has a limited application, as well as it is very known to be very slow. Similarly, Apple has also come out to measure with differential privacy to gather statistics of different items that are getting clicked, or different emojis, different words, popular words, and websites which users are navigating through from iOS and OS X users. They even captured websites where user puts mute, which where they place a button, and you can see here the different graphs in terms of different emojis used by different users. So this is all at local differential privacy level, where noise is added in the place where the information is collected from the user. Similarly, Microsoft has also used Microsoft telemetry application that tracks data of users' app usage. It used two different techniques: one bitmain to collect numeric data, and dbitflip to collect sparse data, which are not so frequent, to build histograms. And those all are at local differential privacy again, where that you can see here that it's getting captured, and there is a amount of noise getting added at the data collectors at the source. And these are the analytics that is getting created, and allow these perturbation techniques, memorization techniques has to be there while building these scalable solutions, because it actually has data from millions of users. Similarly, Snap has also used a local differential privacy-based network using federated machine learning, which most relies on draw and discard ML framework mechanism, where data are collected from the clients and stored into a server, and the server selects one model of the current models available. So it's very kind of a randomized model selection. And once the model is selected, it is discarded, and its aim is to detect phishing URLs. So we have seen such local differential private solutions available. Now let's look at from a mobile user perspective, why differential privacy for local location-based services are important, and how we can build such distributed scalable systems. So it's very important that our users, any users location information is not getting leaked to outside. And unfortunately, it has been seen when we incorporate location obfuscation techniques at the mobile device. So these are not very secure. The geo distinguishability characteristics that are introduced in mobile devices through different apps to protect points of interest for the users are has been able to are leaked outside to the attackers. How? Because there are trajectory informations and there are historical data which are almost related, and they are nearby locations. Even if you add noise, the locations are not that much obfuscated that the attackers are not able to get the actual location. It's possible for the attacker to remap the obfuscated locations, and here you see they get back the main point of interest. So the actual GPS coordinates are getting leaked outside. So that should not be. So when we think of large scale vehicular systems and the automotive systems that are getting designed in the 21st century, we should be able to obfuscate users' location through a well-structured framework and a scalable system. So how do we do that in case of location-based systems? So we have a location-based app at the device and some certain services like data request, profile generator services. Like it can generate different profiles of different privacy level that governs the privacy level. So we can tune and fine tune the privacy levels based on the user profile, based on the location where the vehicle is moving and whatnot. And once we have this location collected at the LBS application, the collected location can be obfuscated through randomization and noise addition, as we were seeing there, and that can be provided to the service provider. Again, the task is of the service provider how he randomly saves this data in his local storage. So there are mechanisms like how do we incorporate privacy, differential privacy at a databases. We'll discuss that. And the service provider has to randomize has to store the randomized data, obfuscated data, and the time also has to be accordingly stored. If he's serially storing the time without obfuscation, but the data is obfuscated, then again there is a chance that get leaked outside. And it should also have a service interface, like it can also, if this location it is there, it can audit again by querying the data that all the data is stored are proper, or is there any something has happened during that time that the data was not collected properly. So the privacy level, the profile generator, differential privacy mechanism, as well as the task of the service provider, it becomes very important in case of vehicular systems. Now let's look into what are the design considerations that we will be taking by designing differential privacy systems. So it is first is the task of the architects and data scientists to understand what is the business problem, what is the data available, whose data are available in the data, what are the confidential information available, and how can we model the different types of different queries or different queries to the database, or the different events that are happening in terms of different sizes, as well as model the privacy budgets for each of these events. So also we have to see if there is a recommendation system, the scalable system we are building. Can we have personalized privacy budgets? So based on the user, type of user or his profile, can we have personalized privacy budget? And when we think about of an end-to-end systems, where do we store the data? We, of course, we incorporate differential privacy at the application level, but is the platform, storage, middleware all abiding by the GDPR? Or is the end-to-end big data processing pipeline having the sufficient security and privacy mechanisms that they honor differential privacy? Is a storage, if it is a streaming data, is a storage technique where we are storing the data and right away are we obfuscating it? Are we maintaining all the ACL rules properly? So it's a differential privacy can alone cannot win or cannot make a system secure without getting the help from middleware, platform, and storage. And in storage, we'll see how database also plays an important role in designing differential private systems. So let's look at what are the different phases of differential private systems and what are we aiming to have that. So one of this is when we design a system, the principal requirement is the feasibility, efficiency, event level privacy, the sensitivity, as well as the scalability. So some of these parameters we have seen how Bolton DP has helped us to get a proper, efficient, and a sensitive, fixed sensitivity driven systems. So how much fast our system is, that will ultimately govern the scalability of the solution. If the system, the differential private solution, it takes a lot of time to train and a lot of time to give back the predicted outcome, then it's not a very good or a choice for a scalable systems. And are the differential private algorithms able to handle numerical categorical queries? Are there data minimization techniques happening when we gather the data from multiple sources? How we are deploying the data? When we think about from the perspective caching or database systems, are we maintaining loose coupling? Are we able to rephrase the queries and see that the overall query budget is maintained? Not only this, for a complex query, not only this individual queries privacy budget has to maintain, but when we sum up the queries budgets, it should be less than the overall query threshold budget. And are we able to decentralize the systems? Because as we have seen that in central systems, the more power is given to a central authority, and that is more susceptible to adversarial attacks. So how do we ensure all these things and design a system? So as we have talked about storage techniques, caching, and database techniques, the one model that comes into very important, that plays a very important role in integrating with last year's big data systems is the Chorus differential private framework that has been developed by Ube. It has been able to execute queries in terms of 10,000s to 1 million in matter of few seconds. Its sensitivity has less than 1% error, and even the medium performance is over 1.7% for over 800 million records. So what does the Chorus framework provide? It has high performance, high scalability, it has high GDPR compliance, as well as ACL rules wherever needed. It supports equi-joins, complex queries, and it is the most important thing, it is very easy to plug in. It is database independent. So we can take Chorus and plug in with any SQL database, be it on Google Cloud Platform or be it on Azure framework. And automatic the DP information rules are there for SQL queries. So based on the type of the SQL queries, there is automatic selection what DP rules will get marked to this set of query. So it is also not that you need to have very complex systems for integrating Chorus. Even general analytics platform can use Chorus, and even non-experts and who have no knowledge much on the SQL part can get and plug in Chorus systems to big data pipeline. Easy integration and no post-processing. So we have talked about seen Bolton DP, how it helps to protect our data by adding noise post-model convergence. But unlike that, Chorus has no post-processing. Now, how does Chorus works? We see that different queries are getting partitioned and noise is added to get differential private results. Split the data into partitions, run query on each partition, and assembling the results. Again, we see a kind of assembling technique that helps to achieve higher performance, higher accuracy, and better results. Similarly, from the point of a perspective of an analyst, when he submits the query on the database, the query itself is randomized with Laplacian noise with a fixed sensitivity to yield a differential private result. And here we will see that there are automatic selection rules, and there is no need for any programmer or query analyst who is working and executing the search operations to rewrite the query. No rewriting engine required. So query submitted, separate partitions, expressions are generated, randomized, and that randomized through the use of Laplacian noise, and the automatic clipping of gradients occur, because again because there should not be any point which contributes a very high amount of data variance to ensure differential privacy. So clipping the average and getting the differential private results. So as we talked about, some of this again characteristics gets highlighted for differential privacy using Chorus framework. We have intrinsically private query, so that can be plugged in with in Google Cloud Platform in with either with Cloud Spanner or Cloud SQL. We have Laplacian data noise we are going to add on the metadata propagation. The metadata is propagated accordingly so that there's no loss of actual information from the metadata. Replacing aggregate functions, it can complex queries, aggregate functions, summations, subqueries, all gets handled through the Chorus framework. The sensitivity mechanism, other mechanisms are there which can help to assure differential privacy based on the type of the query. And the automatic selection mechanism, what mechanisms it gets selected, that also there is a mechanism that it will enable automatic selection. And here the SQL query generator just has to submit the query. And the sampling, aggregation rules, yielding the optimal results for different sets of different varieties of queries, subqueries is the task of the Chorus framework. And it also assures elastic sensitivity, where it has an upper bound on the query's sensitivity, not only to the query's privacy budget, but also the sensitivity. We have seen the two important factors in differential privacy. Now let's look at how we can build such scalable distributed systems in fog and edge computing, because these are two more important things that are using IoT in configuration. IoT devices needs a lot of sensitivity data when they connect those data and send it to the cloud server or to the edge devices. So differential privacy at this level is very important. So one of those things which comes into our mind, that which cloud provider we are going to select. So and it almost comes very easily, that because Google has this TensorFlow network with TPUs, where we can train huge massive scale of data and cluster setup. Can we use the Google Cloud Platform? Yes. Google and Intel has come up with a joint reference architecture that provides many capabilities to do that. So there is seamless data ingestion from the IoT gateway. We will see from the IoT gateway into the Google Cloud Ingestion Engine, and end-to-end data security is enabled, and the devices are protected whenever we collect data from IoT devices. Easy onboarding, easy deployment, robust scalability not in terms of the ingestion pipelines, but in terms of developing the machine learning algorithms, how these algorithms run, how they are, how much accuracy that we are able to get in the shortest span of time. So that is provided by Google and IoT's IoT framework that's developed by Intel. And we also have a support for an analytics engine, like we want to see which cloud devices, which IoT devices are performing bad, good, on the predicting bad, good, is there anything bad happening at the site, or the devices are malfunctioning. All this analytics are captured to either BigQuery or Data Lab or Cloud SQL, where we are storing the data, differential private data in cooperation with the Chorus. So we can develop an analytics engine, and application and presentation layer like dashboards. We can also plug in the Chorus framework not only to the analytics engine, but also a storage engine in the database where we store the actual data. And as we have the pops up like the messaging framework, monitoring, logging, so all this can be treated as a single component of the cloud, where the cloud IoT pushes the data after getting collected from the individual sensors to the gateway and the MQTT bridge. So we can think this as an unified framework with a lot of protection happening, protection ensured in each of these components, the ingestion, storage, application presentation, pipeline, or analytics engine. And it allows capability to train the algorithms in Google's HTPU, and giving more flexibility to the data scientists to compose different differential privacy algorithms and make them lightweight before deployment, so that the resources are not heavily consumed. And if you're thinking of like differential privacy, putting it in terms of federated learning, how do we have a federated learning framework at the edge, mobile edge computing? Why edge devices? Because they offload a lot of tasks before sending it to the before rather than processing onto the client. So some part of the task can be processed by the client, and most of the heavy duties can be processed by the edge servers. So that on the cloud, at the server end, we can have different, as we have talked about, we have seen different ingestion pipelines, the AI, ML, data labs, and other tools that Google, data prep tools that Google offers. In combination with that, we have data processing and deployment services like Kubernetes, Spinnaker, cloud endpoint, DNS, so that the server is also can be deployed in a cluster setup, and the server is capable of handling large load in terms different times of the day, when some of these IoT devices are sending, when a batch of IoT devices are sending data from the edge and to the server. So what we see here, that the server trains a model, and it bifurcates or splits the model in terms of two models. One is sent to the client, another is sent to the edge server, and the client is responsible for extracting the features as in noise and training it to a through a deep learning LSTM or an RNN, and then sending it back to the edge server. And edge server does the maximum processing in terms of learning the network through stochastic gradient descent, and ultimately sending its update to the server. And so the server is averaging the different models that is being sent by the edge devices, which may be like the edge devices may be considering several clients models. So at different times of the day, maybe some of the IoT devices are sending data, some are sending day, some are sending night, some are sending in the during any particular anomaly event. So different types of events are sent through edge server to the cloud server, and the cloud server is responsible for averaging them and determining the final model. And again, through a feedback network, it is responsible for splitting that model and sending it to the client at the edge. So that's how the interchain works. So to leverage, to give clients like more battery, more lifetime, rather than processing, offloading the processing tab to the edge server. And when we talk about, we have talked about like edge computing. Now, how we do it in fog computing. So fog computing also, there's in IoT, any infrastructure which is related, which is based on IoT, we should ensure data minimization techniques that are available to auto encoders. We protect the sensitive attributes. We the first step, the feature distillation, is like the kind of feature engineering, or do the feature assignment, feature cloaking, like converting the features to unique strings through numerous encoding functions, hash functions. And now after feature cloaking, every variables are represented by 0, 1. All the data from the different IoT heterogeneous devices are integrated, aggregated, and they are distilled. Distilled means, again, we apply some kind of filtering technique like min-max filter, what data we preserve, what data we don't preserve, and the edge and the middle edge device, or the middle say processing node is responsible for incorporating noise to ensure differential privacy. And once this data, differential private data, is formed, it is sent to the actual data reconstruction engine, which does the feature building. Like numerous features have been learned from different devices. How do we rebuild and create a distribution function? Like it can be a univariate, or it can be a multivariate distribution. Univariate like logistic regression, or a multivariate using lasso or rich regression, we can build a multiple polynomial term regression model also. So how do we do that in a fog computing environment where there will be a fog node, fog center node, and individual fog nodes? So we can see that in the next slide, and that's how we incorporate distribution of taking data from heterogeneous devices, which have different types of integrity and awareness in their data. Now let's look at this framework. So this is again a fog computing environment where we try to leverage Google Cloud. So we collect the data from different sources, and the aim is to ensure computational efficiency and multifunction aggregation. So we train two different models, and by partitioning the data set into two given model inputs, and then we generate a query-based system that is received from the cloud. So the aggregated results are sent to the cloud. So from the cloud, we should be able to generate a query-based response that is an unique response that leverages the data engines or the data sets that have been split into two different parts. And again, here the important thing is, how do we collect the data? The gateway, we talked about the IoT gateway that is responsible of pushing the data into the global infrastructure. So and then we have the fog center and the fog nodes. The fog nodes actually does this training the data. So fog nodes are nothing but which are close to the cloud service, and they are responsible for storage, training, getting information, and the fog center is responsible for collecting those information and sending it back to the Google Cloud. So this is a highly scalable and elastic platform, and this platform also ensures like aggregated results match the results without privacy. So to conclude, we see that it is not the duty of differential privacy that can ensure end-to-end privacy in a data pipeline, but all the ACL rules, the privacy engines, the GDPR compliance, and the audit rules has to be done properly by the data scientists and the cloud architects who are deploying the models, as well as building the big data pipeline. And we have seen that DP systems are very important in not only in location-based vehicular networking or databases, but they are also important in edge and fog computing, and as well as API-driven SaaS services. And based on the different types of models, we can either use Bolton DP, which is a kind of a, we can say, kind of a global differential privacy model, or even most of these API-driven SaaS services are local differential privacy models. And when we're designing the systems, it's not only an individual task of the data scientists or the big data professionals or architects. It has these concepts, design ideas, and approvals has to be seeken from multiple stakeholders, privacy experts, and security researchers. So it's highly important in this age that we comply with the GDPR and the universal and the unique privacy laws that are being formed in individual countries, so that our system is not compromised and we don't end up paying fines or compromise our annual revenue. Thank you. These are the references. Then go through the references and questions.